Assalamualaikum warahmatullahi wabarakatuh. We are from Group B. So today we are gonna present our group project on fluid mechanics. So first of all, let we introduce ourselves. My name is Muhammad Iqbal Harif bin Hanafi.
My name is Aidil Imran bin Ilas.
My name is Wahijah Salihah binti Mansor.
My name is Siti Syahada binti Sabardi.
And my name is Emily Kavala Lim Ching Hui.
Okay, so our given scenario is about oil droplet rising in drilling fluid. So in drilling mud, small oil droplet will rise. So if the droplet diameter increase, how does velocity rise will change? So our scaling scenario is to predict how the velocity v change when the diameter d is double.
So here is our question. So the first question is identify all relevant variable involved in your assigned scenario. So here our equation, and also we found a seed sample. Next. So for the question 2, write down the dimension of each variable using the basic dimension symbol. So here we have 6 different variable, which is v represent of raised velocity of droplet and has the dimension l to the power -1, t to the power -1, and for d represent for droplet diameter, which is the dimension is l to the power of 1, and for the mu represent of dynamic viscosity of fluid, and for the dimension is m to the power of 1, l to the power of -1, and t to the power of -1. So for the mu represent of density of fluid, which is the dimension is m to the power of 1, l to the power of -3. And next for the mu d represent of dimension if oil droplet, and for the dimension is m to the power of 1 and l to the power of -3. And g represent of the gravitational acceleration, and for the dimension is l to the power of 1 and t to the power of -2. Next. So here we apply the Buckingham-Pi theorem to derive the correct number. So j is m, t and l. So we can calculate k by using seed sample, and j, which is 6 minus 3 equal to 3. So we have 3 pi here. And so for the repeating parameter, we choose d, mu and p, f.
So let's move on to the next question. For Roman 1, we need to solve for pi 1. So we choose the unrepeating parameters as velocity first, v, and then we substitute the dimension variables into the equation, and then we solve for mlt, and we got the value for c1 equal to 1, a1 equal to 1, and b1 equal to -1, and then substitute the value to the original equation, and then we simplify. We got pi 1 equal to vd rho f over mu. Next we solve for the pi 2. We choose rho d as the unrepeating parameters, substitute the dimension variables to the equation, and we solve for the mlt value. So we got c2 equal to -1, a2 equal to 0, and b2 equal to 0. Substitute the value to the original equation, and we simplify. We got pi 2 equal to rho d over rho f. Last we solve for the pi 3. Pi 3 we choose g as the unrepeating parameters, substitute the dimension variables into the equation, and solve for the mlt. So we got c3 equal to 2, a3 equal to 3, and b3 equal to -2. Substitute the values to the original equation, simplify, and we got pi 3 equal to gd to the power of 3 rho f to the power of 2 over mu to the power of 2. So we substitute the value for pi 1, pi 2, and pi 3 to the formula. Pi 1 equal to the function of pi 2 and pi 3.
Okay, so for the next slide, the instruction for us to interpret the physical meaning of each pi term and what it represents in engineering context. So after analyzing, we get pi1 equal to V d rho f over mu, which is represent Reynolds number, represent the ratio between inertia and viscous forces. And for pi2 equals to rho d over rho f, it represent relative density, represent ratio of the density of a substance to the density of a reference material. And for pi3 equals to G d to the power of 3 rho f to the power of 2 over mu to the power of 2, which is Archimedes number. It represents the ratio of gravitational forces to viscous forces. Now for the next slide, the instruction 5 asks to use your pi terms to explain what would happen under scaling scenario given in your assignment. So for our scaling scenario, given governing equation V equals to d to the power of 2g in bracket rho d minus rho f over 18 mu. So from the equation, we let v1 and d1 be the velocity before scaling and density before scaling respectively, and let v2 and d2 be the velocity after scaling and density after scaling respectively. So let x be g in bracket rho d minus rho f over 18 mu, that is assumed to be constant during scaling. Now continue the instruction number 5 from v1 equals to d1 squared x and v2 equals to d2 squared x. We simplified to get a v2 equals to 4v1, and from the simplified equation we can see that when d doubles, v will be quadruple, which is 4 times larger.
Okay, so I'm going to continue for question number 5, which is using our pi terms to explain what happens under the scaling scenario. First, I'm going to tackle pi 2, which is the rho d over rho f. So this represents the relative density, and we know that the relative density will produce a buoyancy effect. So we know that v is dependent on pi 2 from our previous calculations, but it affects v separately from d. This is because you can see in pi 2's equation that there's no d variable, so we know that d doesn't affect pi 2. And if you think about it practically as well, you know that the diameter of the droplet should not affect the densities of either the fluid that makes up the droplet or the fluid that the droplet is in. And we know that d doubling would affect v from the previous calculations, but not pi. Okay, so I'm going to continue for pi 3. So we have our pi 3 equation there, and we're going to do something similar to our governing equation, which is we're going to split it into 2 before and after scaling. And we're going to make the rest of that pi 3 equation represented by y, and we're going to assume that it's constant during scaling. So when we substitute in d2 equals 2 times d1 into the equation, we can see very simply that the pi 3 after scaling will multiply by 8 compared to the pi 3 before scaling. Okay, so we've tackled pi 2 and pi 3, so now I'm going to tackle pi 1. So we know that pi 1 is a function of pi 2 and pi 3. And from our governing equation, we can basically replace some of the terms using pi 1, pi 2, and pi 3. So basically we represent some of the terms in the governing equation with our pi values. And after replacing it, we get to simplify it to pi 1 equals to 1 over 18 pi 3 multiplied by pi 2 minus 1. And we're going to do the same thing, which is isolate some of this and represent it with a variable z. And we're going to assume that's also constant during scaling. So from our previous calculations, we know that pi 2 will be constant. It's not affected by the scaling, and we know that pi 3 multiplies by 8. So from the equation that we've gotten, the simplified equation, we can just substitute in, we can just assume pi 2 remains unchanged, and we can assume that pi 3 multiplies by 8, and if you simplify that, then you can see that pi 1 is also multiplied by 8.
Okay, so for our last question, we must relate our findings to engineering judgment and discuss how our result could impact system design, cost, safety or efficiency in a petroleum engineering context. So first, we go through about our design impact. So, we design more efficient mud circulation system. For example, separated tanks or shale shakers can be used to allow enough time for larger droplets to rise and be removed. And then we proper size tank that will allow faster droplets that produce proper flow rate. And for about our cost, the droplet rising pattern can reduce energy consumption in separation process, which is debris removal. And the efficient separation will reduce the need for chemical additive or expensive treatment process, thus lower the operational cost. And then for the safety, we have proper removal of oil droplet the proper removal of oil droplet improve the stability and performance of drilling mud, so it will reduce the risk of blowout or wellbore instability. And lastly, the efficiency, we have fast separation of oil droplet leads to better fluid recycling and reuse, which is very crucial for maintaining drilling performance. Okay, that's all from our group. Thank you.